Good day. For those of you who do not know me, my name is Douglas Harder. In this topic, we're going to look at authoring an initial value problem solver. Now, in this topic, we are going to look at the weaknesses of the current implementations that we've had up until this point. Now, all of the implementations we've had up until this point are pedagogically useful because they are showing exactly what we are calculating at any one point. And we can then examine these approximations. However, we are going to then consider how we can reduce the work for the user, because a user actually wants to use these approximations to approximate the solution at various different values, but they don't care about the implementation. So we're going to discuss how we can use classes instead to provide a better user interface. All right, the solvers that we have implemented so far are all classic procedural functions. You pass them some arguments and something is returned that the user is intended to use. All of our functions are simply returning arrays, and then the user is expected to do something with these arrays. Now, the MATLAB initial value problem solver ODE45, which uses dormant prints, is similar. It returns matrices, and these matrices can be appropriately interpreted. On the other hand, Maple's dsolve numeric routine does not return an array of data. Instead, it returns a callable function, and all you do is pass it the t-value you want the approximation at, and then it will return the value at that point. And that's sort of actually all the user wants. Hey, I've got this initial value problem. I'd like to find out what the value of the solution is at t equals 1.3 or t equals 7.9. Basically, if we just pass back a whole bunch of arrays, then we're expecting the user to do all of the interpolation or spline calculations. And this could be frustrating. Solution. So instead of just returning arrays, create a class where each instance of this class is a solver for a particular initial value problem, which is described in the constructor. So the function that is the right-hand side of the ODE, the initial values, the initial point, the initial value, all of that is passed to the constructor. The class then has one public member operator, and that is going to be the function operator, which then takes a single argument, t. Now, in the case where it's just a single initial value problem, we'll return a double. Otherwise, if it's a system of initial value problems, we'll return a vector. Now, at this point, all of the data is going to be kept internal to the class, and this includes all the t-values that we've calculated approximations at, and those approximations and corresponding derivatives, which we will use for calculating the splines. Now, question, how far do we have to approximate to? After all, when we call the constructor, they've told us described the ODE and the initial values, but how far do we calculate up to? Well, we don't care, and we shouldn't care either. Instead, we don't know where the user is going to finally end up asking, so instead we do something else. The user is simply going to create an instance, pass the right-hand side function, the initial time value, the initial y value, the minimum and maximum h values, and the epsilon error. That's what the user is going to call, and then on this y they will call various values, and we will only calculate as far as we have to. Now, do we make these calculations absolutely every time? Do we start from scratch and just calculate up until the value the user asks? No, that would be rather a waste of time, wouldn't it? We're not going to do that. Instead, here's our strategy. We will store the t-values and the approximations in a standard vector member variable of the instance of the class. Now, if the user asks for an approximation at a specific t-value, we will see if we've already calculated two approximations on either side of this t-value. If we haven't, it's only at that point that we will start applying dormant prints to continue creating subsequent approximations until we finally pass this requested t-value. Now, any newly created approximations in this process are appended to the standard vector member variable so that we can use these values in the future if the user once again asks for a different value, so that we don't have to recalculate it again. Now, an issue with the naming of the vector class. The standard template library class that is equivalent to a vector or an array on steroids is unfortunately called vector. This was an acknowledged mistake in the naming on the part of the designer of the standard template library, Alex Stepanov. That's okay. He's done many more wonderful things. The fact that he named one class poorly is frustrating, but not the end of the world. There's issues with this naming. First of all, it's a vector class, but you cannot perform vector addition, nor can you perform scalar multiplication. Also, vectors are variable in size. You can resize how many objects are being stored in a vector. So it really was a poor choice because, as you know in linear algebra, if you're dealing in Rn, you assume you are in Rn. You don't resize vectors to move it from R3 to R7 unless you have a linear transformation. So just remember, the standard vector class has absolutely nothing to do with vectors from linear algebra. So just remember that, and that will make a few things easier to understand. That is why for this class I created the linalg package, where I created a separate vector class, specifically one that mimics linear algebra vectors. And this was not done by overloading the character of the standard vector class. Let's look at this graphically. So we're solving or approximating a solution to an initial value problem. Initially, all we store in the constructor is the initial t value and the initial y value, because we don't know how far the user is going to ask. So instead, we wait for the user to make a request. Suppose the user now wants to approximate the value at this t value here. Well, in that case, we will apply dormant prints until the approximation is beyond this t value, and then we will use those last 2 points to compute the spline and return the spline evaluated at the t value. Then, if the user asks for an approximation of the solution at this t value, once again we just start again applying dormant prints until we have approximated a value beyond that last t value. And again, we calculate a spline between those last 2 points and evaluate that spline at the t value in question. If, however, the user now asks for an approximation at some previous point, well, we've already stored all of this data, so we can just recall these last two approximations on either side, calculate the spline, and we're done. Of course, in the very unlikely case that we ask specifically for a point that we've already calculated a value at, we would just return that value, but that's again very unlikely. And again, if the user asks for some other t-value beyond the last one that we've calculated, once again we would just use dormant prints until we have gone beyond that t-value, and once again we calculate a spline between those last 2 points evaluated at the requested t-value. So this is essentially what we're doing here. The user doesn't know how we are storing these values or how we are doing the calculations. We could even use the adaptive Euler-Hoyne method, or we could just use fourth order Runge-Kutta with just fixed interval sizes. However, as we do have dormant prints, we might as well use it. But fortunately, the user doesn't know the underlying interface, and the user doesn't care. The user just creates an instance and then asks us to evaluate the solution at the various points. All right. What's nice about this is the user has no clue as to how these computations are being made. They only know that, oh, I just have to create an instance and call the function operator on it with a specific t-value, and it will calculate the appropriate approximation. At this point, the user will simply look at the description of the package and determine whether or not it is appropriate to use. If not, the user will find a different way of approximating solutions to initial value problems. If the user chooses to use this package, then they could, for example, approximate the solution at, in this case, 0.01, then 0.02, then 0.03, and so on and so forth, all the way up to 10.0. So this would print out the approximate values at those 1001 points. And almost all of those points are probably going to be interpolations or spline calculations, but that's okay. That's what the user is expecting. We are using dormant prints to approximate points to ensure the error is below the required bound, 10 to the negative 4 in this case, and we just then carry on calculating values. So all the values, essentially all the values, are going to end up being interpolated or spline calculated results, and the user doesn't care. So here's an implementation of the function operator. So if we already have approximated the solution up to or beyond the value of t, all we have to do is find the approximations on either side of t in the standard vector class and then return a cubic spline at t. If, however, we have not calculated up until t yet, what we will do is the following. We will create a queue to store new approximations. Why do we use a queue? Because all operations on a queue are order 1. If we try to just keep on appending to the vector class, it's actually going to become very slow very quickly because it will end up being an order n squared overall runtime. So we first start with a queue. So all new approximations are appended to this queue. And then we continue using dormant prints approximating the solutions at new t values and appending these new approximations onto the queue. We keep on doing this until we have approximated the solution at a point at or beyond the value t. Once we have calculated this, we know exactly how many new points there are, And so we will expand the vector class to include these additional points, and then we will copy the data from the queue to the standard vector class. This ensures that all operations are as cheap as possible. Having done so, then we will once again use a cubic spline to evaluate the approximation at the argument t. Following this topic, you now understand how to make interfaces for something like solving or approximating solutions to differential equations much more user-friendly, and you are aware of the IVP class and how it would be implemented, and you are welcome to look at the implementation at your convenience if you wish. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!